Okay.
Done.
Yeah,
That fix it? Awesome. So last time we looked at the first three chapters of the Guardian Tour, and now we're going to look at chapters 4 and 5. So do we all know what Matrix Edition is? Who doesn't? Okay, so I can skip past this first part, but basically adding matrices involves adding all the elements together correspondingly. So in Guardian, we don't currently have a built-in matrix or n-dimensional array type, but we do have part list. And did we talk about part list yet? So part list, we saw it in the Java heat equation. So part list is going to be a class that represents a fixed size list where we can mutate the elements. And this has built-in machinery for splitting up operations on this list across different threads. So we can define an n by n matrix using part list by storing a flattened array of all the matrix elements. So if we have an m by n matrix, we store the elements in a part list of length n, where the first n elements comprise the first row, and the next n elements after that comprise the second row, and so forth. And if you care about formal mathematical definitions, here's one for you. Are we all clear on that part? We're going to store the matrix as one long list. So we're going to encode this in Guardian as a class. We're going to have three fields in our class. We have m, the number of rows in the matrix, n, the number of columns, and data, which is the part list itself that stores the elements. M and n are immutable value types. They're integers, and they're immutable because the matrix is never going to change dimensions, right? You add two matrices, they come out the same dimensions. Because I tried to be cute and make int render as code, because the type in Guardian is int. Yeah, so it's a stylistic choice. It kind of looks ugly, but too late now. So part list is a vault type, meaning that it has interior thread-safe mutability. So our class itself has to be a vault type because it can't be a value type because this is a vault type, right? The strictness of the sharing policy of the class can't be stricter than any of its fields. I sure can.
Right, or less, right.
The I guess strict can be defined in two different ways. So let me give you a better definition. So the strictest in the sense that it is the hardest to satisfy is value, because that means state that is totally immutable. And because we have a vault class in here, it's a looser constraint than value. And so our class can't be a tighter constraint than this field, right? If we only had values in here, then this could be a value type. But because we have a vault in here, this can only be unsafe or vault. Do we like that? Okay. So here's what our class looks like. We declare it as a vault class matrix. We have m int, n int, just our two immutable integer fields. And then we have data, which is a part list of real. Real is a double precision floating point number. So we're going to add a constructor to the class that initializes the matrix. There's going to be code in a second. To initialize the part list, we have to call the part list of function, which takes a size, and then we have to give it an initializer function of type int to t. So this function is just going to say, we're going to give it whatever index of the part list we want to instantiate, and this function gives us back what we're going to put there. It'll make more sense when we see the code. And since our matrix type is going to be two-dimensional, we want to say that the constructor for our matrix class is going to take an initialization function of type two ints to a real, where the int arguments are the row and column indices. And because there's a bit of a hiccup in the Guardian compiler, you can't actually pass a lambda to a constructor directly. So we have to make a function that calls the constructor. Sorry about that, but it's not too bad. So here's what we have. Right, we have our matrix class, we have our fields, we have our constructor. We declare them like this. We say the access level and then new. So in Java, this would be the name of the class would go here, but in Guardian, you just write the word new. We have m int n int as arguments, and then our initialization function, which we write like this. This is just a lambda that takes two ints and returns a real. And then we initialize the fields just like in Java, and then we call part list of to initialize the part list. We're saying it's going to have n times n elements, and we're going to say we want to set the ith element to the result of the initialization function that we got in the constructor. And the two arguments are going to be I over n and I mod n, because that's how we've formulated the flattened matrix representation. Right. So if we call this again and again from 0 to n times n then I will have the values 0, 1, 2, 3. So this will increase, 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 increase. Then this will go down to 0, and this will increase by 1, and then so forth. And then of is just going to take the same arguments as the constructor and just call the constructor and return it. And once I fix that problem, then this won't be necessary, but currently it is. Do we have any questions about this code right here? Is there any syntax that is alien to you? Okay. So first, we're going to define a method on this class that just prints the object to the console. So to access the elements of a part list, we have to use the runParted method. This method is going to transparently partition up the elements into different chunks. And then for each of those chunks, it's going to run a task on those partitions in parallel. So part list runParted takes 4 arguments. You have the chunk specifier, which is just either you say, I want this many chunks and let part list cut it up for you, or you can give it an array of tuples of integers to say specifically, I want this exact range and this exact range and this exact range to be a partition. I don't think you will use this version at all in this class. We added this to make quicksort work. So for your purposes, you just pass the number of chunks that you want, and then part list splits it up for you. Then you pass in the number of ghost zones. We're not going to talk about this right now, but this is the same concept of ghost zones that we talked about with the heat equation, if you remember that. And so in this particular problem, this is just going to be 0, and we can omit the argument if it is 0. Then we have to pass in at least one part intent. This is going to specify which part lists are involved in the given computation and whether we're reading to them, writing to them, or allowed to do both. And again, this is just like we saw in the heat equation. And then finally, we have to give it a task. This is just a lambda. It's going to accept a number of part views corresponding to the part intent that we passed in. Each of these views is going to correspond to one slice of the part list, and we'll have reading and writing capabilities according to it. And in Guardian, we don't have to use get and set on these views. We can just use square bracket syntax to subscript into these like any normal array type. So this is a lot all at once, but when we look at the code, hopefully it will make more sense. And if it doesn't, you can yell questions at me. So here's our print method. And it has to return a future because runParted itself is asynchronous and also returns a future. And mustConsume says that we must do something with this future, remember? So we are calling runParted. We only want one partition, which just means do something with all the elements in some thread. And we're going to say we're going to read from our data. And then this is the view. And then we're just going to iterate over the m and n directions and index into the flattened array to get the value at this I and j coordinate. We're going to print it out. And then after every row, we're just going to do a println to add a new line to the output. Is this good? Okay. And right, we have to return this whole thing because of mustConsume. So here is our code so far. We'll paste this into the notebook for you. We also added a program with an entry function. We are just initializing a new matrix of 3 by 3. And see, here's what the initialization function looks like. We're going to say the element at column I, row j is going to be, row I, column j is going to be this function. So I plus j, and then we have to add 0.0 because I and j are integers, and the function wants to return a real, and so we have to just coerce the integer to a real. Some silliness that will hopefully be fixed in some future version of Guardian, but right now you just have to floatify your integers. So here's what our matrix looks like. You can see it's just the row and column index added together. So 0, 1, 1, 2, 4, 3, right? And we do in fact see this output. Questions before I move on? Is this better? There's some colors. Maybe you like that more. Oh, but we can't see it all at once, can we? Is this too small?
I
Okay.
can see it.
There's nothing really parallel going on this yet.
No, nothing parallel is happening yet. We're just trying to make this matrix class exist in some way. Currently, all we can do is construct it and we can print it, and printing it is asynchronous. Hooray.
I guess I don't understand the part where you say, can't pass something line built with, gradually. I know it's kind of a bug in the compiler, but we that function was like, it's called of,
Yeah,
but partless of is the only thing I see.
this is matrix of.
Oh, there it was. Okay.
Yeah. So ideally, what we'd want is to be able to say, and then just this thing. Right. We want to be able to write that, but currently the compiler just has a bug where that doesn't work. That's all. Are we all done staring at this? Okay. So now we're going to write a method to add two matrices together. And in this case, rather than modifying the matrix in place, we're going to return a new matrix containing the sum. So add won't touch the two addends. It will only give us a new matrix with the result. So we're going to have an async function add. We're going to take the other matrix because it's a member function, and we're going to return a future matrix. First, we want to check to make sure that both matrices have the same dimensions, so we can just compare the m and n fields of both addends. Right? We check against this m and other m, and then this and other n, and then either of these don't match, we just call error die, which will throw an exception that kills the program, and we just print out an error. And when you use error die, you have to import error. That should say goo4 error. That's a typo. Next, we're going to create a new matrix to hold the result. So we're going to call matrix of to obtain a new matrix object. We're going to pass in the dimensions of the result, which is just the dimensions of both of the addends. And the initialization function is just going to set every element to 0 because we're going to then write into this matrix. So since we're going to be calling run parted for this computation, we need to decide how many partitions we want, because this is going to correspond essentially to how many threads are going to be running the task. So in this case, for simplicity, we'll just take the larger of m and n. So whichever dimension is longest, that's the number of threads we're going to split up the computation between. So we're just going to assign that to a variable called threads. To use mathmax, we need import goo4 math. Now we can call run parted to compute the sum of the matrices in parallel. We need to read from the two addends, and then we need to write to the result. So this is how that looks. We call partlist : run parted. This is the number of partitions. There are no ghost zones, so we just skip it. We read from our own data. We read from the other matrix's data, and we write to the data of the result. And the parameters are ourselves, the other matrix, and the result. And look at that, we can just write it like this. So this is a feature of Guardian called auto-vectorization. And what this is going to do is it's going to let us write loops over elements of array-like things with this syntax. So in this case, the two dots in the square bracket means a slice of all the elements. So this is saying all the elements of result are equal to the corresponding elements of self and other added together. And this will compile basically exactly to this. Because 0 to result writable size is all the elements of result, right? And then we just put I in there. Any questions about this auto-vectorization syntax? I agree, it is nifty.
Any other language have that?
I'm sure they must exist, but Julia has it, yeah.
What was the question?
The question was, do any other languages have this kind of syntax? And the answer was Julia. And there
Well,
are
yes,
plenty.
and Python and Fortran, they all have similar things.
Python has that?
That has like photos of that?
No, I don't think so.
I don't think Python has this.
It's like
Yes, it
NumPy.
does. It has, well, it doesn't have that exact thing. You put a colon there instead of dot dot.
That's also.
Yeah, but
NumPy.
Okay.
You can like. If you do it like colon, row, you do like self.
Yeah.
Colon, it would just append the lists together. It wouldn't have each element.
Okay.
I couldn't hear that.
You get a list on the left side, you get a list on the right side, but it's just like the whole list, not.
Right. So Tristan, right?
Oh, yeah, right.
Yeah, so Tristan is saying that if you write this in Python with colon, then it won't work how we think it does. It won't actually iterate over these element-wise. It will just append one slice to the other slice, with at least Tristan thinks.
I'm pretty sure that's not true. I'm pretty sure I've used it with array notation like this in Python before. Python
think
is
NumPy.
actually, what's that?
I think NumPy supports it, not Python itself, but NumPy
Yes,
sort of
okay.
overloads it.
I don't think of Python and NumPy as distinct. So
Okay, that's
um,
kind of fair.
um,
Python is a bit of an overgrown calculator, if you ask me.
but I think the first array syntax was done by Fortran. But anyway, Guardian has a little bit of a new spin on it, and you'll see that.
Yeah.
And Julia dealt with a macro, so it's kind of cheating if you want to think about it.
Yes, Julia cheats by using a macro, by some definition of cheating. Okay, so run parted returns a future, as we know, so we have to consume it, as we know. So because this future, it represents the completion of all the tasks initiated by run parted, its completion means that the result is ready. So we can just simply return the result at this point. So we call then to do something after this run parted completes. And then at that point, we simply async return the result. So now here's our full program. This is a lot to fit on screen, so I'll paste it into the notebook and then you can stare at it there. Right, so this is just our matrix class from before. Here's the add method all at once. So just to recap, we check the dimensions, initialize our result matrix, decide how many partitions, and then over those partitions in parallel, read from both matrices and write to the result the sum of self and other. And then once that's done, we async return the result. And then in main, we just get an A and a B, where A is the coordinates. A is initialized so that the elements are the coordinates of the elements summed together, and B is the same thing, but they're subtracted. We're going to call A dot add B, then C, that just gives us the result C of adding A and B. We're going to print out A, we're going to print out B, we're going to print out C, and then we're going to return. And that is in fact what occurs. And you can stare at this and convince yourself that this matrix is in fact the sum of these two. Are there any questions about matrix addition, this code, anything like that? Okay, what's your kind of slightly unrelated question?
Solid color. Because when I have something like writing comments and stuff, it looks like it's not a comment because keywords and stuff will like change color.
Right. So the question was, why is the syntax highlighting in the notebook so bad? And the answer is because it's trying to syntax highlight Python, because remember, we just hacked on this functionality to a Python-based notebook. So unfortunately, no, you can't make it look any prettier. I would have to dig into Jupyter Notebooks and figure out how to make the syntax highlighting work better. Yes.
Active and then becomes better like this.
There's a thought. Let's try that. Yes, that works. Okay, cool.
What works?
If you put pounds in the comment on each line, then the comment has a color.
Oh, yeah.
Instead of the double,
Yeah.
but it doesn't.
Well, it'll highlight it, but then Guardian says, no, that's not a comment. Just in case you're wondering, Guardian supports single line comments with 2 slashes and block comments like this. It's just like Java or C.
Correct. There.
That's right. Those are the correct comment characters. No questions about matrix addition? We're all going to ace the quiz about matrix addition.
It's not today, so by the next time we have
It's in my backpack, actually. No. So, okay. All right, so let's move on. So now we're going to talk about the heat equation again. I will skip past all this because we already covered it. And just as a reminder, we want to basically run this computation over all the elements of an array, stepping forward in time progressively, one step at a time, until we have decided that we have reached the time step that we want to reach. And the way that looks is something like this, right? All familiar to us? Okay. So we're going to use part list for this, unsurprisingly. So we're going to define a function that takes one step forward in time. So it's going to take 2 part lists. One contains the previous time step that we're evolving from, and one is used as a destination to write the values of the next time step into. So here is our program, namespace heat, value class heat. We have a static field that just represents our constant C. We're going to set this to 0.49 for numerical reasons. This is our function step. It's an async static function step. We take 2 part lists. We return a fute void. And then when this feature completes, it means that we've written something into destination. First, we're going to handle the periodic boundary conditions. Remember, this is the property that once we go left off of the end of the array, we wrap around to the beginning and vice versa. So what we're going to do here is we just want one partition because one thread can do this. It's just 2 copies. We're going to both read and write from the source. And we call our view all. And we say we set the 0th element of all to the second to last element of all. Because remember, the last element of all is one of the ghost zones. So we want the last actual value. And then here we set the last value, or rather we set the ghost zone at the end of all, which is the last value, to the second to last value of all, which is the first real value, or second to first value of all, rather. The second value of all actually is a better way of saying that, huh? So this is going to be similar to how we used run part in the previous section. We run one task over the whole list, and I already said this. So next we're going to implement the stencil function to actually evolve in time. And this has to happen after we move the ghost zones around. So we're going to call .then on the boundary condition code to schedule this run parted call to happen after this is already completed. And this is what it looks like. So we say we want two partitions. We want one ghost zone. We read from the source and write to the destination. And we just call source and dest the same thing. So we just shadow those variables. And then we say for every element in destination, we set it equal to the corresponding element in source plus heat C times this thing, which is, so now you can see we have the same auto vectorization syntax as before, but now we have offsets. So the two dots here, 2 times source, that's, remember, this is when we're reading from the same position at the previous time step. But here we're saying we need to look to the right, which is 1 dot dot, and 1 to the left, -1 dot dot. And the reason this works is because these views are always 0 based in their index. So no matter what partition that we're on, source of 0 is the 0th element of that partition. And so source of -1 is actually the first ghost zone because 0 represents the first actual non-ghost zone value in the slice. So by specifying these offsets, we can concisely express this whole sliding window looking to your left and right to read the neighbors thing that we have to do to make the heat equation work. Is this syntax in particular clear to everyone? Is it unclear to anyone? What do you mean, like if I wrote 0 here? No, this double dot just means all the elements. So double dot is normally the thing that has, so normally you write the start index, double dot, the end index, but you can leave off the start or the end or both. And in this case, we're leaving off both, which means all the elements. But in this case, we're leaving on the starting index, but leaving off the ending index. So now this starts at 1 and ends at the end. But this starts at 0 and ends at the end. This one starts at 1 and ends at the end +1, because Guardian will try to make it so that this size agrees with whatever's on the left. So if we start one element to the right of the current position, then we will include the rightmost ghost zone. Because remember, we specified one ghost zone, which means that both of these lists have one extra element both at the end and the beginning. So remember, this is going to compile to a loop. So you can imagine this is for I in 0 to destination size. And this is destination of I, of I, of I plus 1, of I minus 1, of I. Yes.
Set it to either 2 elements, 3 elements.
You can set it. So this parameter, the second parameter to run parted, that controls how many ghost zones there are. Yeah. That, what do you mean? One zone is just one array element in this case. So you can't have one ghost zone that's bigger than one element. You just have more than one ghost zone. Yep.
I guess I'm looking at the words.
Yep. Okay, so let me back up a bit. I guess I didn't make this clear. So when you have a run parted call with reading and writing, then the ghost zones change the ranges of reading and writing. So when you're writing to a view, that view, you can't write to the ghost zones because you handled the ghost zones up here. So the range of values of destination that you can write to is smaller by one ghost zone, so smaller by two elements than the range of values you can read.
It might be good to scroll back up to that picture in your
I will
notes.
scroll up to that picture, right? So we have one ghost zone, which means we have this extra zone all the way on the left and this extra zone all the way on the right. And we're telling one-parted that when we tell one-parted that we're writing to something, it's going to give us this range. It's going to exclude the ghost zones. But when we're reading from something and we have ghost zones, it will include the whole thing, except that the zero index corresponds to the same thing that it does on all of them. So zero always points to the first element that you can write to.
It might be good to also highlight what an individual thread can read and write.
I think I just did.
You know, you did the whole thing, right? You
Okay,
highlighted all the way
two people are
across.
talking at once. Hang on. Reagan. So it's always a spaghetti noodle. The donutness is something that we're simulating by handling the boundary condition. So if we didn't do this part, then the ghost zones would be fixed. They would never change. So that is a valid boundary condition, fixed boundary condition. So we hold the ends to one value, and that's the default, you could say. Does that make sense? Yeah.
And what I understand, that percentage are actually.
Yeah.
Part of specifying one, so all listening, right? Element zero. will actually-
So element zero is this. It's the zeroth real element in the sense of not being a ghost zone.
And when we follow this, read that number will correspond to the same number.
That's right.
That's called 0 minus 1. Then we're looking at this.
Right. So we can go if we have a read view, we can go leftward of zero. So -1 will correspond to this ghost zone here. And we can go one past the end as well, because that's the ghost zone on the right. Yeah, you can't write to them. You can see them only when you're reading. And if you don't have any offsets in your auto-vectorized syntax thing, then you never even see the ghost zones, because remember, Guardian tries to make the sizes of these ranges agree with what's on the left. And since we're writing to the destination, then zero will always be this, and the values that we see. So thread 1 sees these values in destination, and thread 2 sees these values in destination, but each of them can see one extra value from the source, because we need to be able to read the ghost zones.
You have to highlight the it should be 9 to 5 gets highlighted as for ghost zones, because 5 is a ghost zone for thread 1 and 4 is a ghost zone for thread 2, if you want to think about it that way.
No, that's not right.
Well, the read for thread 1 should include zone 5.
Yes.
Yes.
Yeah, so it's not a ghost zone technically, because it's just shared memory. But yeah,
Yes.
sorry, I highlighted one off. Yeah, thread
yeah,
1.
it should be 9 to 5 is the reading range, if you
Yeah,
want
this
to
is
call it
the
that.
reading range. It's expanded by 1 in either direction. And
Right.
thread 2, it's this. Yeah, sorry,
Yes.
that's my mistake. But the writing is correct. This is what thread 1 can write. This is what thread 2 can write. And you'll notice that because the writing is constrained, then that's why it's safe to read outside of the available memory that our thread should have access to, because at this point, this thing that we're reading from isn't getting written to at all. Yes, Lucas, you have a question.
So if I want to set the ghost zones to a specific value, how can I do that? Because the writing view doesn't let me do it, right? If I understand correctly.
So you can do that if you have a read-write view.
What was his question?
So the question is, if you just want to set the value of the ghost zones explicitly, how can you do that? Because the right view doesn't let you target the ghost zones. And the answer is you use read write. And when you have a read write view, there are some restrictions. So when you have a read write view, Runparted doesn't let you specify a number of ghost zones. You're only allowed to have a read write view of part list if you're not doing any fancy ghost zone stuff, because otherwise, for example, if we allowed that with a ghost zone, then we'd be able to read and write to this range, and then thread 1 can write to thread 2's memory, and that's unsafe. Right? That creates a race condition over this element. That's a very good question. Yes.
Because only one thread is allowed to write. But how do you guarantee that the thread is going to be the right? Isn't it? I guess I'm confused about how there's the possibility that thread can get right far back to get
For the read write one, you mean? Or for everything?
No, for the second. Like the few seconds.
Right. So the reason that works is because the source list we can only read from. Nothing can write to this. And the destination can only be written to, it can't be read from. Yes. Yes. And actually what happens is for one step, so we have two lists at all times. And then for one step, we say read from the left one and write to the right one. And then the next time step, we do the opposite. So we go back and forth between these two buffers because we only care about one time step previously. Any more questions? We're all happy about this. It's okay if it's confusing. It is a lot of information, but so please continue to ask questions until there are no questions left to ask. Yes. Yeah.
That was,
So it's technically implemented as just a whole bunch of generated code that takes every combination of possible read and write part intents up to some limit because of a limitation with Java. The plan is to engineer a way for it to actually be var-args. But for your purposes, these are var-args, except you can't have more than 5. But in of course, the final version of Guardian, these will be proper var-args, yes. It's just that to do that, you essentially need something akin to C++'s templates, and Java does not have those. And so Guardian essentially needs to have some features of C++ templates. And if you've used those, you can imagine how hard that might be to add. Any more questions? Okay. So now we're going to tie the ribbon on this step function by calling then on this single time step and then just doing async return. Now in main, we're going to write some driver code. So like I said, we're going to cycle between two arrays. Each one is going to take turns being the source and destination until we've evolved all the time steps. So n is the number of points in the grid. It's a very small grid. Steps is the number of time steps we're going to take. We have U1 and U2. These are just going to be the two lists that we're cycling between. We're going to initialize them to this. So it's just going to be really cold at one end and really hot at the other. And because it's periodic boundary conditions, we expect everything to flatten out eventually in the limit. Then we're going to print the first part list. I don't think I talked about this. I'll show you in a second. This is just a function I wrote that prints a part list. It's not doing anything fancy. So we print a part list. This function returns a future. And then after that part list is printed, we have a call to marching 4. So from 0 to the number of time steps, this is the step index. So which time step we're currently on. If we're on an even numbered time step, we call step where U1 is the source and U2 is the destination. But if we're on an odd numbered time step, we use U2 as the source and U1 as the destination. Yes. So marching 4 will run the body of this loop asynchronously, but it will only run one iteration at a time. So it'll run the first iteration, and then when it completes, it runs the second iteration and so forth. Right? Because the time steps do need to happen in order. And because marching four's body has to yield a future, we yield the future given by step. So this is saying whenever this step function completes, that iteration of the loop is complete and we can do the next one. And then after that whole thing finishes with then, we print the part list again. This is showing the final evolution. And then after that, we're going to call this verify function, which I'll show you in a second. This is just going to take the final grid and the number of elements and check to make sure that the evolution looks like what we'd expect it to look like, which is all averaged out, flattened out. And it's going to give us this Boolean verified, and we're going to check to see if it's true, and then we can print whether or not we succeeded, and then we have an async return. And then here's the whole program. So verify, okay, let's look at part list first. So print part list is a run parted with one partition. So one thread is just going to print out all the elements because otherwise keeping them in order would be obnoxious. We read from the whole list. If it's empty, we print this square bracket thing. Otherwise, we just sort of make a string that we build up with all the elements and then print it. This should be pretty self-explanatory, I hope, but are there any questions about this function? Yes. Yeah, it's not, well, yeah, I mean, I guess in theory it could block a little bit, if it's waiting for IO. We don't have an asynchronous version of println. No, yeah, it's for our purposes, it's not asynchronous. There probably should be an async version of this for file IO though. We just currently don't have one. And then verify.
I added a file IO thingy, didn't I?
You did, but it's not asynchronous.
Right. Okay.
It's an unsafe type. So
Yeah.
we have a print writer class that you can use to write stuff to files, but it's unsafe. So you have to synchronize on it if you want to share it between threads, or if you just want one thread to have it, then that's fine. So anyway, don't worry about this. Trust me, this is just the value that we expect to see. We have a tight tolerance and a loose tolerance, and then for every element in the list, we're just taking the average of every element. So first we're seeing if every individual element has the same value of the expected value with the loose tolerance, and then we're checking to see if the average of these is not too far from the expected value either. And that one is a tighter tolerance because the average, we have an average of many values instead of just one value, because one value can be subject to floating point round off, but that round off error gets averaged away if we look at the whole list. Are you all okay with verify? It's pretty straightforward too, I think, if you ignore the magicness of this expression. Okay, so I will plop this all into the notebook. Right, so we start with this up ramp of temperature, and then we end up with everything more or less averaged out. And, there are some little aberrations here because of floating point round off shenanigans. This is why we have the looser tolerance for checking the individual array elements, but for the whole array, that round off gets sort of smoothed out. And I think that's all I have in terms of guarding material. Are there any questions about the heat equation? Are there any questions about Guardian at all? Yep.
Hope it's fine, but, very hard. But like, explain how we would.
Okay, so I guess we don't have an example of that, do we?
What's the question?
the question was, can I show them how condition variables work in Guardian? And the answer is like, I don't think we have an example of that, but I can certainly show it. So actually, this is a good opportunity to look at something else real quick. So on this website, if you go to just the root of the website, you will see this. So this is cct.lsu.edu/tilde/morris/guardian/docs. And Introduction to Guardian is the pages that we've been looking through in this class. Core Guardian Concepts is a bit of a higher level summary of a lot of the Guardian concepts. So sharing policy is explained. The capture rules are explained. Async functions are explained. And then here we have a reference of all the classes and functions in the standard library. So if we want to look up how condition variables work, we can find cond here, and we can read about how it works, and we can look at all the methods. But the basic way it works is, say we have a guard var. We can create a condition variable based on one or more guard vars, in this case, just one like this. Is it guard new condition? Yeah, new condition. So this is a condition variable that has access to this guard var. And then we can say guard run condition. Is it run con or run condition? It is run condition. And we give it cond. I have to remind myself how this looks.
Is it possible
Yeah.
that like those, functions, if you like clarify or make them look down, but it's like, it isn't that.
Yeah, so this is just, so these are the base versions up here, right? So you can imagine run guarded just takes GV, and then, but you can give it GV1, GV2. This is just saying that you can give it up to n type parameters, up to n different. Right, this is the varargs thing again. It looks kind of goofy because it's so big and it doesn't all fit on the page. I guess I would just have to format this, but like I can try this. I'll get back to the condition variables in a second.
I wanted to ask a question myself of the class at this point. So I have on the schedule that we go off and study other things next week, but I'm wondering if you would like to continue doing a workshop, you know, sort of in class time with the server and trying to understand how to program in Guardian better, or if you would prefer to hear about what was the next thing I had? Transactional memory.
I'd rather do workshop.
One vote for workshop so far.
All right.
2 votes for workshop.
It just
Yeah,
basically.
but
What else is there to Guardian? What else would we be covering in the workshop specifically?
Well, what we would try to do in the workshop is I would have a bunch of we would try to come up with a bunch of small programs and work through them together to, you know, give everybody a chance to try and code in this, because, you know, hearing somebody talk at you and saying this is how a language works is a much different experience from trying to actually make it work. I mean, things you thought you understand somehow frequently don't work out once you try to actually use them, right? So I thought that what I would do is we would come up with a set of small examples, and I would say, here's one, and I let you work on it for, 5 minutes, and then we discuss how it was actually done, and do that sort of several times.
Yeah, I think I would like that.
We have unanimous-ish consensus.
Okay. I kind of suspected I would, but I wanted to ask.
Yeah.
Yeah, in worst case, there are 4 votes for workshop and 3 votes against, but yeah.
Yeah, okay.
Now remember, that the more material the class covers, the more things you're gonna have in the final.
That's right.
You know, if I were you. Well, this is gonna be on the final, and I would like to know more about it, and also it's interesting.
Yeah.
I like all our time.
I'm glad you guys think it's interesting.
It's a good paradigm, it takes a minute for me to wrap my head around it.
Yes.
It's staying interesting until we get up in the assignment.
Well, don't forget, tomorrow at 7, we're going to be at Highland Coffees too. So we're trying to give you as much with the Guardian homeworks as possible because we want you to have fun with it, quite frankly. We don't want you to pull your hair out over it. So don't be afraid to ask us for help, please. Anyway, Tristan, does this help you with the signature? Yeah.
It's not like just one line, like.
I got to figure out a way to make it look like that in the website.
Fix that. This is an example of how it's gonna be.
I might do that. Anyway, so condition variables. Then you just give it the conditions, you give it. So the lambda is going to take the guard vars that we created the condition over. So we created it over G, so we're going to say we take G. And in here, so the idea of a condition variable is it's something that you want to run only when some condition is met. And in this case, the condition has to be some function of the guard vars that you're capturing in the new condition thing. So what you do is, you say, let's say we want G to be 0 here. So if G get is 0, then we do some work. And then we say done. And if it's not 0, then we want to try this condition again later. So we say retry. You could also say yield false instead of retry. Or instead of done, you could also say yield true. Right. So done and retry are just aliases for returning true and false. And then to retry tasks that are waiting, if you want to retry one task, it's the condition variable dot signal. If you want to retry all the waiting tasks, it's all.
So say we're running these in the parallel loop, right?
Mhm.
I'm trying to remember what this, like the end of the video. But like, I know like in the docs it said there's like run condition and run condition future. So what's the difference between those things? Like run condition for those like.
Oh, yes.
What was the question?
So the question was, why is there a distinction between run condition and run condition fute? And the answer is that there isn't anymore, and that this is slightly outdated. It used to be that this version without fute returned void, and the one with fute returned a future void. But now there's only run condition, and it always returns future void. So that's a good catch. I have to update this website. Yes. So the only reason we have the one that returned void instead of future is just because we didn't have the must consume rule working properly. And so we needed an escape hatch from it, but now we have it working properly, and so we don't need it anymore. So it's always going to be this version that returns a fute void. It's just not called run condition fute anymore.
So red is run condition. So you should, would that just be run, is it guaranteed that this is in, like safe as well? For the G, there's, access to that, right?
Yeah. So it will run these condition tasks as if they're tasks that you pass to run guarded. So this G here is a var of int because there's an implicit run guarded in here.
That is my life so much.
I'm happy. I'm happy to have made your life easier. Any more questions? We have 8-ish minutes before class lets out. If there are no more questions, you can skedaddle.
I guess one more question is like, when it runs condition, it's basically like wrapping a run guarded as well.
Not really. It's its own thing, but you can imagine run condition as a souped up run guarded, right? Instead of running the task once, it's going to run the task as many times as it takes. But every time it runs the task, it's always going to have to acquire the guard first. So even if there's something else that acquires this guard that isn't using condition variables, it still has to be synchronized over the guard.
Our guard or run guard that like can retry, then also like can be awakened.
Yes. Yep.
Determine all.
Yes. So yeah, it's 1-to-1. It's just that retry looks nicer. So what happens is when you call signal, it just plucks one task that's waiting to be retried and then retries it. Signal all, retries them all. When you first call run condition, it will always try the task once before being signaled because it might be able to run immediately. Is essentially what? No, I guess you can kind of imagine like while condition is false, then retry it, but it's not really a loop. It only gets retried when you call signal. So if you don't ever if you call run condition and give it a task that calls retry instantly and then never call signal, then that task never gets run again. So Guardian doesn't necessarily save you from that. The issue with what we're trying to do, which is formal program verification, is that to solve it for any program, you need to solve the halting problem, which is a famously unsolvable problem. So with condition variables, we haven't yet figured out a way to prevent you from shooting yourself in the foot with them, but it's something that we'd like to work on for sure. So you do have to be careful with those.
It would run immediately and check the condition, or like, if you're expected to check the condition.
Yeah. Well, you always have to tell it. Yeah. Well, you always have to say whether you retry or not. And the expectation is that you will check some condition and then decide based on that condition. You could, in theory, check anything excuse me, you could check anything that this lambda is allowed to capture, right? So if you have some value type or vault type that's sitting up outside of the lambda and you want to capture that and then check that to determine the condition, that's fine too. But if you want to synchronize these conditions for whatever reason, if your condition touches a guard var at all, then you have to do it this way. Because run condition or run guarded are the only ways to get into a guard var. And if you try to put a run guarded in here, right, remember this property of guards that when you call run guarded inside of a nested run guarded, the guards don't get inherited. This is an entirely new temporal scope. So this is removed in time entirely from this. So we couldn't put G here and then check G like that. We have to do it this way. Anything else?
Just compile a type static and try and do that.
Well, yes, because then we can't return from the lambda. Right? So let's say we want to try and check some condition bad. Oops. right? What do we do here, right? Because if we write done, that's equivalent to yield true, and yield targets this lambda. It can't actually do anything to this lambda. So the compiler doesn't catch it so much as you just can't write it.
And, yeah, so it would still, it could still do that, but it just would do. It would just do it and it wouldn't be able to calculate.
Right. You can write this, but it can't influence the condition task itself because it's in this nested run guarded call, and so it's removed in time. So that's what the whole idea of temporal scope is. So that big fancy word. It describes this property of this not being able to touch the scope that encloses it.
Is that one of the main motivators for making it?
Yes. So one of the big things is enforcing these temporal scoping rules and not letting you capture things across temporal scopes that aren't safe to capture. Right. So if we have some unsafe type here, like if we have if I try to capture C in this thing, then this thing that runs at some future time can touch the same memory of this thing running now. And that could create a race condition if this thing happens to get kicked off while the enclosing thing is still running. Two more minutes. Ask your most burningest questions now or forever hold your peace. And by forever, I mean like for a day.
What's a good starting point for the homework?
Which homework?
Diamond philosophy.
Yeah. Did you do the guiding philosophers like the first assignment?
That's what I said.
Honestly, just look at that, see how it will, you know.
Yeah, here's the guide source.
You see.
Does it answer your question?
Right.
Okay, I'm not sure how to answer it, so I would defer to Dr. Brand if you want to ask him, but because
I
I don't.
can't hear the question.
So the question was, what's a good starting point for the current homework?
You mean the dining philosophers?
Yes.
Yeah.
Well, I mean, you got to figure out how, how you're going to represent the chopstick, and how did we represent the chopsticks with lock-based code?
Chopsticks as locks.
We are
I can't-
representing chopsticks as locks.
Right. So what do you think you're going to use to represent the chopsticks in this code?
Guards.
There you
Guards.
go.
Oh, you heard that one.
Yeah, I heard that one. Yeah. So so that should give you some notion of how to start, right?
Yep.
Yep.
And I suspect, well, I feel like the problem in one sense is easy, but it's difficult because, it's a new language, and the new language is supposed to help, but there is a learning curve. So we'll see how that works.
Okay. Wait, just to clarify, this homework is being written in Java or Guardian?
Is this homework Java or Guardian?
Uh,
I thought it was
what did I
Java.
say? I think I said specifically. Hold on.
I thought it was Java, it's just I was asking.
Yeah, it was probably Java. You're right. You're probably right.
I think the goal was to give the Guardian homeworks today, or I don't know.
Yeah, the Guardian homework should be next. I think. Yeah, the intent was for you to code it in Java using guards.
Okay.
Okay, class time has ended, so you may skedaddle.
All right, see you guys. Virtual next week.